Here in 15 video B, we talk about the complete state of stress in pressure vessels. In order to understand the state of stress in a pressure vessel, the last thing we need to know then is what is the stress in the thickness direction. We'll call this sigma of T. Note that the thickness direction is the same as the R direction in pressure vessels, which can be a little confusing, and we'll revisit this a few times. So if we look at this, we have a pressure vessel. Then on the outside of the vessel, the only thing creating any stress there is atmospheric pressure. And atmospheric pressure we refer to as zero because, as we have throughout this course, we haven't paid any attention to it. But inside, there's a pressure P that's pushing on it, as we noted. And so whereas the outside is zero, the inside pressure is P. However, we've said that R over T is much greater than 1. This was our definition in order to have thin-walled pressure vessels. So if R over T is much greater than 1, then that means that P is much less than PR divided by T. And so because of this, we just approximate sigma as T equals 0 over the entire thickness, although it's actually changing from 0 to P as we go through there. It's always insignificant compared to the stresses that we've calculated that are within these pressure vessel walls, the circumferential longitudinal, or the stress that we see in the plane stress that we see in a sphere. So our total state of stress now is a biaxial state of stress. For the sphere, we have PR over 2T in each of two directions and then 0 in the thickness. For the cylinder, we have PR over T in the circumferential, PR over 2T in the longitudinal, and then 0 in the third. So because this is biaxial stress, we are already aligned in the principal angles, and we know that we can just say sigma 1, this is tension, so it's the greater of these. It's PR over 2T for the sphere, and sigma 1 would be PR over T for the cylinder. Then we ask, what is the maximum shear stress? So now we finally have to consider both in-plane and out-of-plane shear stress. So if we have an element up here, we can rotate it this way. And rotating it that way is looking at the difference between sigma C and sigma L. And so tau max in that case will be half the difference between those sigma C minus sigma L over 2, which will equal, when we plug in these values, PR over T times 1 minus 1/2 over 2, or PR over 4T. But now what if we look at an element that's right here along this cut? So we had said that this is sigma C, but in this direction, we have sigma T, which is essentially 0. Notably, we could also, if we made a cut in this direction, put an element in here where we have the sigma L in the longitudinal and sigma T this way. It's a little hard to see this because this didn't actually have a cut here, but I'm saying if we had a cut here, we would see that in that plane. So we can also then have these out-of-plane tau maxes that we've illustrated here, where we have sigma C over 2 because we're subtracting 0, that is sigma T from it. Sigma C over 2 is PR over 2T, and then we also have sigma L over 2, which is again PR over 4T. And tau max is going to be the largest of those, and the largest of those is this right here. So that's our tau max in the cylinder, and we've just rewritten that here. Now in a sphere, we have essentially the same thing, but we really only have two to consider. The in-plane is the difference between the two stresses together. So in plane, tau max is 0. And then out of plane, will just be the difference between either of those and 0, and so those will be PR over 4T, because we are saying that it is either of these divided by 2. And so again, this then is the maximum. The out of plane again is the maximum. And we had warned that this would happen. We have here biaxial stress where both of the principal stresses are the same sign, and so out of plane is larger. Finally, we have an example. So our example is that we have a stainless steel material. It has an allowable tensile stress of 1000 megapascal, and it has an allowable shear stress of 450 megapascal. It must be used at a pressure of 18 megapascal. And our question is, what is the maximum ratio of radius to thickness for tubing used for this purpose? So what are we asked to find here? Well, we're asked to find a ratio of R over T. And what kind of vessel is this? Well, we said it's tubing. So tubing is a cylindrical. So what are the stresses? Well, for a cylindrical, there's sigma L equals PR over 2T, and sigma C equals PR over T. And so we know some information here because we know P, but we don't know R over T, but fortunately that's what we're trying to find. So that looks like we're getting close, but now we need to compare the allowable tensile stress to sigma 1. Remember, sigma 1 is the largest. We're already aligned in the principal axis, and we need the stress to be less than that to avoid failing. So we have the pressure, 18 megapascals, times R over T, which is what we are trying to find, must be less than ATS, which is 1000 megapascals. Then we also want to compare the allowable shear stress to tau max, and we had said for a cylindrical pressure vessel that the out of plane was equal to half the difference between the circumferential and 0. That is, the tau max was equal to PR over 2T. And so we can then again say 18 megapascals, but this time we divide by 2, and then we have the R over T that we need to find and say this is less than 450 megapascals. And we can rearrange that to say that 18 megapascals times R over T must be less than 900 megapascals. So then we're saying, well, which of these is more restrictive? Well, it has to be less than both of them, so it must be less than 900 megapascals, and so then we will rearrange this equation here to say that R over T must be less than 900 divided by 18 megapascals, which is just equal to 50.